Hello everyone, I am Xinwei. Today I will present Witcher systematic crash consistency testing for non-volatile memory key value stores. This is a joint work from Virginia Tech and Stony Brook University. NVM has been considered to revolutionize the storage stack by providing the following properties. Persistent, bite-adjustable, low latency, and high capacity. However, NVM programming is hard because you must guarantee the integrity of your data even under power failure. Formally, a crash consistent application can recover a consistent state from persistent memory in the event of a crash like a power failure. In the current architecture, a cache is volatile. Volatile cache states may be lost upon a crash. So controlling the durability and the ordering for cache life is the core in the NVM programming. To support NVM programming, Intel provides two primitives for controlling cache-like eviction. Once a data is evicted from the cache, it becomes persistent. The first primitive is flush. It writes back a cache line from the cache to memory. The second primitive is fence. It provides ordering guarantee between flushes. Let's have an example here. After the first line is executed, x equals 1 reach the cache. Then a flush is executed. It issues a write back from the cache. But after executing the flush, x equals 1 is not guaranteed to reach the memory. Only the following fence is finished. Then x equals 1 reach the memory and becomes persistent. Then y equals 1 has the same flow here. So by using those two primitives, NVM programs eventually control durability of updates and ordering of durability without unnecessary persistent overhead. We did an NVM bug survey on open source NVM software. There are different types of persistent bugs. Persistence ordering bug. It fails to enforce that A must be persisted before B. Persistence atomicity bug. It fails to enforce that A and B must be persisted together. Persistence performance bugs such as extra flush and extra fence. Among those three bug types, let's dive into the details of the persistence ordering bug. The persistent ordering bug, which is caused by incorrect persistent order. I will use a real example to illustrate it. The bug comes from a persistent hash table called level hash from OSDI 18. For each key value pair, it has a valid flag called token in the persistent hash table. If you look at the insert code here, it writes key, value, and a token, and then called flush and fence. It looks correct. It presses order rise in the same order as the rise happened. However, it may incur a problem. Let's have an example here. After executing this, the three rise, it is possible that the token is evicted from the cache. If there is a crash happen then, after recovery, only the token is persistent, but the key and the value are not. If you look at the read code here, for reading, it checks the token to be valid first and then compares the key and the returned value so that users may read garbage values because the token is persisted, but the key and the value are not. The root cause of this bug is the incorrect persistent order. The right figure shows the fix. It first writes the key and value and then persists the key and value. After that, it writes the token and then persists the token. In this way, when the token is persisted, the key value must also be persisted. Here, I need to emphasize that it requires application-specific knowledge to detect such bugs. There are two prior solutions to detect persistent bugs. One solution simply tests all possible NVM states, which is too expensive and not scalable. The other one relies on user-provided oracles to prune the test space. This solution needs manual efforts, which is error-prone, especially for devising application-specific oracles. So the challenge here, how can we prune the test space without user-provided oracles? To address this, we propose likely-correctness condition inference. Our key observation is that the programmers often left some hints on what they want to ensure in the source code. Take the read code example again. The hint is that it checks the token first and then with the key and the value. More specifically, there is a control dependence between token and the key value. This tells us that when the token is valid, then the key value pair must be persisted. So the correctness condition is that persisting key value should happen before updating the token. Having this inferred likely correctness condition, we will only test the correct state violating it. Take the right code example here. We apply the inferred likely correctness condition and check whether there are violations. And we found that the token can be persisted before the key value pair, so that we will test the correct state where only the token is persisted. In this way, we will automatically prune the test space by inferring likely correctness conditions. Suppose we found a potential crash inconsistent NVM state using the first key idea. The challenge here then is how to automatically validate a crashed state. Prior solution relies on user-provided oracles, which needs manual effort and it is also error-prone. So to address this, we will use output equivalence checking by leveraging the durable linearization. Durable linearization means upon a crash, an NVM program should behave as if the crash operation is either all or nothing. So let's use an example to illustrate here. Suppose we have a crash execution. It has 3 operations: insert key with value 1, delete key, then insert key with value 2. The crash happens at the 3rd operation. All semantics means that all those 3 operations have been successfully completed. Nothing semantics means that the first 2 operations have been successfully completed, but not the 3rd one. Instead of comparing those 3 images, we run each image with the same test case, which is the get key operation, and then collect the outputs. Based on durable linearization, a consistent output should match either value 2 or none. If the testing outputs match neither of these 2 outputs, such as value 1, it indicates that there is an inconsistency. That's a bug in crashing operation. In this way, which will automatically validates a crash state. Based on those 2 key ideas just presented, we designed Witcher, a new systematic crash consistent testing tool for NVM key value stores, which takes a program and a test case as input. A test case is a sequence program operations. The first step is to trace the memory accesses and then infers likely correctness condition from the trace by using programming analysis. After that, Witcher constructs a set of crash NVM images violating the conditions. Then Witcher performs output equivalence checking to validate if the condition violation is a true bug, which also detects performance bugs as a bonus by analyzing the trace. We evaluate Witcher with 20 NVM programs with diverse implementations. We test each application with 2,000 randomly generated key value operations, which detected 47 correctness bugs from 18 programs. 36 of them are new bugs. All the bugs have been confirmed by the developers. The detected bugs have diverse impacts, and there are different fixing strategies for fixing those bugs. Here, I need to emphasize that all those bugs fixed are complicated and require deep understanding of the applications. I'd like to show one new bug from PMDK memory allocator detected by Witcher. In this code snippet, it changed the older header first and then writes a new header. However, the fairly atomicity algorithm of PMDK requires that the new header should be initialized before the older header is changed. To fix the bug, we need to flip the order of those 2 functions. Detecting this bug requires application-specific knowledge, which is able to detect this bug by using likely correctness condition, inference, and output equivalence checking. We also evaluated how effective Witcher can prune the test space and thus improve the scalability. First, we compared the number of the tested crash states between our detector and the exhaustive searching approach YAT from ATC14. We used the same trace with 2,000 random operations. As shown in the figure, the test space of YAT is several orders larger than our tool. We only test when there is a crash condition violation, significantly reducing the number of test space, yet detecting many bugs. Second, We also compare our tool against a random searching with 100 million possible crash states. Testing each 100 million crash states cost around 1 week. The result shows that randomly 100 million case can only detect 1 or 2 bugs that which are detected, which shows the random searching doesn't work and which are effectively detect many bugs. In conclusion, developing a correct NVM-backed crash consistent program is hard. The proposed tool, which infers likely correctness conditions to prune test space, performs output occurrence checking to test inconsistency automatically. In evaluation, which detected 205 cracks and performance bugs in NVM-backed key value stores and the PMDK library, which can effectively detect NVM bugs without a user-provided checker, without a test space exploration problem.